All right, sounds good. So we're gonna get started. First of all, the DataCam group was approved. So I think I sent emails today. So you should be able to access our group, and then you should be able to see 3 assigned modules there for courses. 2 of them are not required. So if you don't have much R experience, I recommend you to try the introduction and the intermediate. But I know that some of you actually did it before. So yeah, feel free to check those out. Those are not required. But the third one, Introduction to the Tidyverse, it's required for credit just by completion. So make sure that you do it by the date that indicated the deadline. And if you have questions or problems accessing it, just let me know. And yeah, so I think that's for the DataCam. It just got approved this morning. And we're going to continue the interpretation of probability and Bayes rules. Continue from last time. So this was the last page. I think we ended last time. So again, the inference procedure of Bayesian inference has 3 general steps. Okay, before seeing any data, we have a prior probability. Later on, we're going to start to talk about prior distribution. Okay, but for now, we stay in the field of field probability. And let's say we just have a hypothesis. So that's why we have yeah, and then we're going to collect data. Okay, and after that, we're going to use the data. That's why we're having a conditional probability statement here. And we're using the data that we collected to update what we believe about the hypothesis. Okay, so that's the general procedure. And of course, down here, I mentioned about the sometimes non-intuitive understanding or interpretation of the frequentist p-value, because p-value is really, well, given the hypothesis, especially in this case, given that the null hypothesis is true, then you have a probability statement about the data itself. Okay, so we think as a Bayesian in this course, so we always think about the hypothesis as well. I mean, the probability of the hypothesis, and data is just like trying to help us to sharpen our belief once we see data. All right. So as a simple example, many of you probably have seen this before, or like similar style that we're trying to look at how to figure out using Bayes rule to figure out, well, if you have someone who have a positive test outcome, say for breast cancer screening, what will be the probability that this person actually has disease? Okay, so we're just gonna start with a toy example here, just get us up to speed of doing a little bit of Bayes rule computation. All of this are discrete. Okay, you only have outcomes yes or no, right? And yeah, I should say you have test outcomes of positive and negative, but also the truth, whether you have it or not, is also binary. Okay, so here is a 2x2 binary case that easy to work with and make sure that we all understand Bayes rule in the discrete, most simple case. So American Cancer Society estimates that about 1.7% of women have breast cancer. And also, from other sources, mammographs correctly identifies about 78% of women who truly have breast cancer. So that's among the people who actually have cancer, the test will have a positive rate of 78%. But sometimes things like mammograph in this case have a 10% false positive. So false positive is the person actually doesn't have a disease, but the test is going to come out as positive. Okay, so let's just think about, well, if we're going to do this through a Bayesian point of view, how are we going to come up with a probability statement about, well, what if this person does come out to have a positive test? What's the probability that this person has breast cancer? Okay, so in order to do that, so let me maybe set it up. So you already see that on the screen. We're doing this, determining the prior, doing the data, all that. But at the end of the day, the goal of the analysis is that if someone does have breast cancer, or sorry, does have a positive test outcome, so that's being conditioned, plus sign using, we use plus sign as the positive outcome, test outcome, and then this person does have breast cancer. Okay, so it's a conditional probability statement here, okay? And our goal is to try to come up with this probability. So I'm gonna just put it over here, bottom, so that's the goal. So the Bayesian inference, like we said earlier, we're first gonna come up with the prior probability. In this case, if you think about it, it's going to be the prior probability about having cancer. Okay? So on this page, we're trying to come up with this. And this is what this question is about. Prior to any testing and any information exchange between the patient and the doctor, what probability should a doctor assign to a female patient having breast cancer? You probably don't remember the number that I showed on the previous page, but I think it's the American Cancer Society is saying that 1.7% of all American women have breast cancer. Okay, so this is what we're going to assign for the prior, because prior belief should be we should have it before we see any data. And in this case, we don't know anything about this woman. And we are saying that no testing, no extra information exchange. So the best guess of this person having breast cancer will be the prior, and it's just going to be the population percentage. Okay, so we have P, probability of C. So C stands for cancer, is 1.7%. So this is what we have for the prior. So again, prior is given when you have no idea about, like before seeing any data, and then you will try to use your best guess. All right, so it's 1.7%. And now I'm asking you to calculate the posterior. And we got another student coming. Okay. And remember, what we are trying to do is we're trying to compute the conditional probability of somebody having a positive test outcome, given that information was probably that this person has breast cancer. And we earlier determined this probability is 1.7%. Okay, so that's the prior. And the other two probabilities that I mentioned earlier in the first set of the slide, I doubt you will remember them. I don't have those. I did write them down. I'm just going to write it out for you here. So the other two things is, remember, among all of the people who do have breast cancer, the test correct rate was 78%. And the other piece of information is that, in fact, this person does not have breast cancer, so I'm just going to use no C here, but you can have false positive rate. And for the mammograms, they are 10%. So these are all the information that we have here. And the thing is, keep in mind, we're trying to get this. And Bayes rule, I'm going to write it down here for you here as well, so you can, and you probably have it on your notes as well. But Bayes rule, generically, we have probability of A given B should be probability of A and B over the marginal probability of B. Okay. So I'm going to stop here for a little bit. Some of you might have experienced before. If you not talk to your neighbors, try to work it out a little bit more before we look at it together as a class. I will walk around as well. Okay, so I think we probably all come to roughly the conclusion, not yet soon. So anybody who wants to talk about how you solved it, like the thought process, et cetera, and how that you're using the Bayes rule in particular in this case. Anyone? Yeah.
Okay, so like the numerator of that Bayes rule, like equality, you can just say that that is equal to like if you switch them around, like the probability of A given B times probability of A, and like in the context of this problem, that would just be the probability of a true positive times the probability of someone having breast cancer.
So you're trying to put it over here, right?
Yeah.
So it's C and positive, and then the denominator will become marginal probability of the positive, right?
Yeah.
So good. So the thing is, I guess earlier many of you were not too sure how to get this marginal. So how to get this marginal in this case?
So you can like think of the two distinct possibilities, either that you have cancer, or that you don't have cancer. So first choose that you have cancer. Well, then what is the probability that it was positive given that you had cancer? Then choose, and then we're going to add because it's like distinct, right? Choose that you didn't have cancer. And then what was the probability that it was positive given that you didn't have cancer? And then you should cover the whole space.
Right.
Positive.
Yeah, good. So this is in terms of terminology, this is the law of total probability. Okay, you're trying to come up with the marginal probability of some event. And what you can do is you can have a partition of like the space. We're going to talk about the detail when we get to the probability review as well. In this case, in order to think about the marginal probability of having a positive test outcome, it's possible that you have cancer and test positive. It's also possible that you don't have cancer but test positive. Okay, so already following the speaking just now, I already wrote it down in this way, but really it is plus and C plus and no C. Okay? So the law of total probability is that, well, you have to think about the partition of the other case, and then you'll be able to get the sum of all of the joint to get the marginal. Okay? But of course, once you get to the joint can be obtained. So it's always Bayes rule. You use it backward or forward. So in order to get plus and C, you can use the conditional plus given C times the marginal of C. Okay? And then to get plus and no C, you can do the conditional plus given no C times the marginal of no C. Okay? So in this context, what do we have? The let's see. So we do have this two given here, and they're useful because exactly we are trying to work with the positive, positive outcome case. So the only thing that you need to come up with here is that the marginal probability of no C. So this is another key definition, complementary event, okay? Because it's either C or no C. So you have to do 1 minus 1.7% to get the marginal probability of no cancer. So if we follow all of this information, what we're going to have, so it's 1.7% times. So I'm just following like my write-up of this order. And then conditioning on having cancer with positive test outcome is 78%, right? And then I do 1 minus 1.7% times the 10% that we get over here. Okay, so once you do this, you're going to get the marginal. And then you do the marginal as the divide. And the top, the numerator, in this case, is just this particular first term, right? So that's why in the discrete case of doing Bayes rule, a lot of times you will see that like one term of the denominator will be the term on the numerator, okay? And that's just one particular case that you will be able to get. But this is pretty generic. So the answer, let me see, just the numbers itself is 12% if you already did the calculation. This makes sense, right? So make sure that we understand marginal probability, conditional probability, and joint probability, and how to manipulate through Bayes rule. All right, good. So this is the case that if we don't know anything about this person, so we start with 1.7% prior to this person having breast cancer, and then this is the posterior probability. And the plus here is the data.
Excuse me. I'm sorry.
Go ahead.
Is that supposed to be 0.017 or is that 0.0017?
Yeah, I think you're right. Sorry about it. So typo. But I think the final answer is right.
Yeah, the final answer is right. Yeah.
Okay. Thank you so much.
Yeah.
Yeah. All right, so typo, just ignore that. But the posterior probability should be 12%. Okay, so this is saying that if we don't know anything about this person, we start with the prior, which is the population probability or percentage, and we now observe a positive outcome for this person. And then we update our belief about whether this person is having cancer or not, because it's a positive outcome. So our posterior probability in this case jumps up from 1.7% to 12%. Okay, so some of you might think, okay, 12% is still not very high. I mean, if you decide or if you determine that you already have it, you have to go through all of the chemo stuff and that. So people might want to do another test just to double check that if this person does indeed have the breast cancer. And if you do that, and in particular, I should mention, so let me Yeah, let me go to this exercise first. So now this person, we already know that the first test is positive. And before going to the second screening, what do you think the prior distribution now before the second test would be? So I list 4 choices here. The thing is, we did one set of screening already, okay? And we got a posterior. So now we're trying to do another test. And what would you think the prior probability for this test will be? Yeah, what?
0.8, 0.12.
Mm-hmm. Will be 12%, right? So the reasoning, first of all, like typically when we're talking about sequential updating, that you're doing multiple tests, you're collecting data sequentially, the previous posterior will be your new prior. Okay, so that's always the rule of thumb. And for this case, or like in many situations as well, the intuition here is that now you're working with this particular woman who is different from an ordinary, like randomly chosen woman out there who should have 1.7%. But for this woman, she already tested positive in the first test, so she's different. Okay, and we're trying to incorporate the information that we already learned from the first test. And that's why we're using the previous posterior as the new prior. And so you start with 12%, and that will be your new prior here. And let's suppose that this person again tested positive. Okay, so this should be straightforward, but just try to work it out again. The probability that we have earlier, I think is, so here the prior becomes 12%. If the person has cancer, test positive rate is 78% as before. And then no cancer, false positive was again 10%. Okay. So keep in mind here we're collecting the second round of data. Okay. And the data tells us it's another positive, which is another plus. So the question for you is, what will be the posterior probability in this case? It's going to be very similar to the procedure that we did before. But once you get the answer, just think intuitively, even before you're getting the answer, do you think it's going to increase or decrease?
Increase.
It's going to increase, right? It's going to keep going up. So I guess A and B are out. C and D is just more about doing the calculation correctly. So just try that really quick. It's going to be very similar. So it's going to be faster than just now. All right, so C and D, which one did you get?
D.
D? Mm-hmm. Okay.
D.
Thank you. All right, so I just put down the calculation here. And so again, earlier we said that intuitively already know that's going to go up because we're having a second test coming up positive. It just, we don't know how much exactly. And this 52%, well, is higher, more than 50%. But if you still think you want to do a third test, then this becomes your new prior. Okay, so that's what we mean by sequential updating. So earlier, this slide I skipped because I want to get to the exercise directly. But a lot of times, as you collect data along the way, you can iteratively collect data and then iteratively update your belief. In this case, it's always from the prior to the posterior. Okay? And the previous posterior becoming new prior. And we update it from the previous iteration. All right, so just to recap, we always try to take advantage of prior information, sometimes with a previously published study or another physical model. In this case, for the toy example that we did, it's always, well, I have a test of positive, so I have a new belief about this case, right? And then as more tests are coming in, I keep sharpening my belief about this hypothesis, this person having breast cancer. And Bayesian inference naturally integrate data as you collect it. So you update your priors to the posterior. And overall, again, we always try to talk about the conditional probability or distribution later on about what is the conditional probability that given your observed data, what's the probability that the hypothesis is true, and comparing to the frequentist definition of p-value, which is the opposite. Okay, so keep those in mind. They're the biggest difference. And of course, you might be wondering, okay, prior does play a big role. right? Whatever prior that you have might change. Especially just look at the two examples that we had, the sequential update. So before we start, the prior was 1.7%, right? And then we go to a 12% posterior if you have a positive test, right? And then for the second test, I know it's a sequential, so it's always within the framework, but I just want to use this as an example because if you remember, the data is the same in each case, right? The data is always a positive test, right? And the data is coming into play in the form of like the test accuracy, false positive rate and stuff. So it's the same data, okay? But what prior you have is going to obviously change a lot in terms of the posterior that you have. Okay, so this is.
I have a question actually.
Yes,
Yeah. So how is like, so in this example, say, right, like you did one test and then you did another one, right? How is this different from doing two tests simultaneously?
yeah, great question. So I left a homework question for you all just to think about, well,
Okay, sure.
yeah, no, but because it's a natural question to ask. And in this case, I will be imagining that you're going to get the same. So like whether you get
Right.
two positive tests in a row or one at a time and updating sequentially, you're going to come to the same result.
Sure.
Okay. Yeah. But I give a yeah. So take the time to do the homework question so you will see it more clearly. But the goal here is that, well, with the same data, either you come in sequentially or you come as a batch. The sequential update will get you to the same result.
Right. Thank you.
Yeah, thank you. Yeah. So in this case, as you can see, that prior does play a big role. Data plays a big role as well. It's just like in this particular toy example, we don't see it that often. But regardless, the posterior is determined by the prior and the data together. Okay. Rule of thumb is if the prior, so we say here, watch out, a good prior helps, a bad prior hurts. But then the prior matters less the more data that you have. So that's why in a lot of theoretical definition or proof that yes, we do approach probability from different angles. I mean, Bayesian and frequentist. But the thing is, a lot of the properties of the Bayesian methods, you will be able to enjoy those frequentist properties if you have large sample. Okay? So no matter what, you come to the same conclusion if you're a large data set. And then of course for us, a good prior hurts, a bad prior, good prior helps and bad prior hurts. So we want to make sure that we get useful prior. And throughout the course, you will see that, well, sometimes you probably don't have any information or like you don't have strong beliefs, so you might just give a uniform or like what we call like a weakly prior, like a very weakly informative prior that you want to have the data to decide for you what the posterior will be, okay? But in general, of course, the more data you have, the better. But Bayesian methods is useful, especially when you have very little data, okay? Because you can use the prior to help a lot if you have a good prior. So remember last, I think on Tuesday, we talked about, well, we're flipping coins for 3 times and you get 3 tails in a row and then we're trying to figure out the probability of having heads, right? So that's a small sample, only 3, and also a p-hat, sample proportion of 0, and that will be really hard in the frequentist point of view. But then for Bayesian, even with small sample size, you will still be able to incorporate the prior, so you're slightly better off. You know. All right, so okay, so that's for the Bayesian interpretation of problem in Bayes rule.